Ask my instructor 13.9.27. Find the values of L and G that maximize this utility function subject to the given constraint. Give the value of the utility function at the optimal point. We're going to use Lagrange multipliers, so I set up that the gradient of f is equal to lambda gradient of g, and g equals 0. So I take that constraint and I turn it into a function where the level curve g equals 0 gives me that constraint. So we need to set up the equations based on the gradient of f equals lambda gradient g and the equation g equals 0. So you should end up with 3 equations when you're all done. And these are the 3 equations that I get. Looking at this, I suppose there's a number of ways of doing this, but what popped out at me is the fact that my third equation is a simple linear equation. Linear equations are definitely all right by me. So I'm going to start with the third equation, and what I'm going to do is I'm going to solve for L. Once I solve for L, I'm going to use that expression in the first 2 equations. And this is what I get. I changed my negative exponents to fractions, but this is what I get. Now, the really nice thing by doing that, I didn't know that this would happen. A lot of times in math you just have to follow your nose. But what happened is I now have 2 equations with 2 unknowns, and that's an ideal situation. So what I'm going to do, and again there are different ways to handle 2 equations, 2 unknowns, but looking at these 2 equations, it looks like the easiest thing for me to do will be to solve for lambda in each equation. After I solve for lambda in each equation, then I can have those 2 expressions equal to each other. So if one expression equals lambda, which is equal to a second expression, then those 2 expressions are equal to each other. I don't know if that made any sense, but hopefully the picture will tell you what I'm trying to say. So I set the 2 expressions equal to each other and I solve for g. Now we actually do not need to know what lambda is. Sometimes we find lambda because that's helpful, but finding lambda is not necessary, and if you can do the problem without finding lambda, all the better. So I'm just going to forget lambda now. It was only designed to help me. But however, I do want to know what L is. I have found that g equals 3/2, and what's L? So when g equals 3/2, L equals 3, and I'm now ready to give the value of the utility function at the optimal point. The utility function at that optimal point is 15 radical 2. I'd like to talk a little more about what's going on here. First, I'd like you to look at the surface of the utility function. So this is the utility function viewed as a surface, where I have L and G in the horizontal plane. The dotted blue line is the constraint that was given to me. I'm looking for the highest value of u such that G and L are on this dotted blue line. Just to be clear, this dotted blue line is in the GL plane. So G and L values must come from this dotted blue line. And I'm looking for the highest utility given G and L are coming from this dotted blue line. And you can kind of eyeball it to see where it might be. I'm using level curves to help us see it a little bit better. And again, the dotted blue line now is solid because I have everything in the LG plane. And then I have the level curves of U showing. And the optimal point is where U equals 15 radical 2. Now, they've not drawn a level curve for U equals 15 radical 2. So it's not on a level curve, but that's visible, but there is a level curve for that value too. So anyway, L equals 3 halves, G equals, L equals 3, G equals 3 halves is the optimal location, and it gives a utility of about, let's see, radical 2 is about 1.4, so 15 plus about 6, about 21, something like that. Let me know if you have any questions.